Except with the lightest crudes, the products of refinery distillation are not yet ready for the market. They need to undergo further treatment. In particular, the heavy residues must be converted to lighter, more useful products. This chemical conversion is called cracking. Cracking reduces the molecular size of the hydrocarbons. It breaks up long-chain molecules into smaller ones. There are three basic kinds of cracker used in refineries: the thermal cracker, the catalytic cracker, and the hydrocracker. This is a thermal cracker. It converts by the application of heat. The furnace heats the feedstocks up to 500 degrees Celsius. The feed is usually one of the heavier residues from distillation. Precise control of time and temperature influences the cracking process. From the reactor, the cracked stream is passed on to a fractionating column, where its components are separated in the familiar manner. Most of the hydrogen is taken up in the lighter of the molecules produced by cracking. The residue looks much like coke. It's formed of hydrocarbon molecules with a very high percentage of carbon. Typically, the most valuable product fraction from thermal cracking is for gas oil, used in diesel engines. Thermal cracking is efficient and relatively cheap, but it's not particularly good at producing the lightest fractions, such as gasoline. That's better done in a cracker which uses a catalyst. A catalyst provokes or speeds up a chemical reaction. Here, into beakers of dilute sulfuric acid are placed strips of zinc. Then to one of the beakers is added a solution of copper sulfate. Almost immediately, a chemical reaction is initiated between the acid and the zinc, with hydrogen given off. Without the copper sulfate as catalyst, this reaction would take much, much longer. In the refinery, crackers which use catalysts are called catalytic or CAT crackers. The catalyst used is essentially of silica and alumina. It's finely powdered so that it can be moved much like a fluid. And like all catalysts, it will help to bring about chemical change without in the end being changed itself. The feedstock, typically a lighter distillate from vacuum distillation, is heated. It's mixed with the catalyst in the riser. Feed and catalyst proceed together to the reactor vessel, where they're separated. The used catalyst goes on to a second vessel to be regenerated. Then it's fed back into the riser to start its work all over again. So there's a continuous flow of both feed and catalyst. The actual cracking takes place in the riser in only a few seconds. The reactor vessel is where the cracked feedstock and the used catalyst are separated. Carbon is formed on the catalyst, making it less effective. In the regenerator, at great heat, this carbon is burnt off, and then the catalyst recirculated. The cracked feedstock is drawn off from the reactor vessel into fractionation columns. A typical yield from the process shows a strong bias towards light gas oils and especially gasoline. This is one of the very newest CAT crackers. The regeneration chamber for the catalyst stands out. There will be a high yield of the lighter products from the fractionation columns, including gases for the plastics and chemical industries. But gasoline is the principal product. The gasoline from a CAT cracker is of higher quality than that from straight-run distillation. Let's see how far we've come. After straight-run distillation alone, this was the yield of fractions. After vacuum distillation, this is the improvement. After thermal and catalytic cracking, these fractions are further refined. Throughout, we've assumed that the original crude was a middle-range grade. Despite all the refining processes used so far, there's still a residue of heavy fuel oil. And it's still quite big, certainly too big for the market demand. To reduce it further, we'll need a different kind of chemical conversion. The third kind of cracking process involves the addition of hydrogen. This is a hydrocracker. A catalyst is still used, but the chemical reactions it initiates take place in a high pressure of hydrogen. There are usually two reactors. The first removes impurities from the feedstock, the second cracks this purified strain. In a hydrocracker, there is no residue. The entire feedstock, a fairly wide range of distillates, can be converted into the required product range. So hydrocrackers are very flexible in operation, but they are costly to build and operate, though improved catalysts and cheaper hydrogen have lessened these costs. And they won't process this, the heaviest of the residues, rich in carbon but poor in hydrogen, unwanted and to all appearances unusable. Until now. A new plant in the Netherlands takes the use of hydrogen conversion in refining to its ultimate conclusion. It's called Hycon, and as a feedstock it uses the unusable. The key processes take place in a succession of reactors. A heated stream of hydrogen-rich gas is mixed with the feed flow of oil. The reactor vessels are under great pressure, and the reactions within them will create additional heat. In the first reactors, the catalyst's principal role is to remove unwanted metals like nickel and vanadium. The catalyst is designed to encourage such metals to be deposited on it. Gradually, the metals are removed. They're characteristic of the heavy residue feedstock used in Hycon. The flow of feed goes on to a second group of reactors. A regular constituent of the heavier crudes and residues is sulfur, and it's in this second group of reactors that most of the sulfur is removed as the gas hydrogen sulfide. Then the hydrogen conversion of the feedstock is completed, much as in a hydrocracker. And this is what Hycon produces, a fluid mixture of hydrocarbons not unlike one of the lighter crude oils. From this crude, a whole range of products can be refined. To separate the crude out into usable fractions demands a succession of distillation processes. The first stages of distillation produce gasoline, kerosene and gas oil. Then a high vacuum unit takes the residue to produce a feedstock for cracking. Again, gas oil will be an important product. Nothing is wasted. Using Hycon on our middle-range crude converts the maximum possible into the fractions the market wants. Even with the heaviest crudes, good results can be achieved. Chemical conversion of oil doesn't only entail cracking. Products can be improved by causing chemical change within a fraction. The process is called reforming. This reformer is used to enhance the quality of gasoline. It uses platinum as a catalyst and is called a platformer. The feedstock is typically a broad gasoline fraction from straight-run distillation. It's mixed with a hydrogen-rich gas, heated and vaporized. In the reactor, this vapor is passed through a catalyst. The chemical reactions which occur change the molecular structure of the hydrocarbons. The molecules are reformed. In particular, the straight chain molecules are converted to ring or branched molecules. This process is repeated through 3 or 4 reactors. These can be side by side, or in the most modern platformers, stacked one on top of the other. Following the reforming, the hydrogen-rich gas is separated out and recycled. The remaining mixture, now called a platformate, goes on to be distilled in a separate column. The resulting fractions provide high-grade blending components for aviation fuels and especially gasoline. Platforming gasoline improves its octane rating. This in turn assists improved engine performance. A refinery not only separates out petroleum products physically and converts them chemically, it must also clean them. The major impurity is sulfur. This is a hydrodesulfurization plant. It removes the sulfur by converting it into hydrogen sulfide. At special sulfur recovery plants, this hydrogen sulfide is in turn converted to sulfur. Sulfur has many uses in industry. These key facilities form the heart of a refinery. Many more are needed to support them, and all must function without harming the environment. Plant to purify the products, plant to blend and prepare them for market, plant to make lubricants, waxes and solvents. There must be tanks to store the crude oil on arrival, tanks to store the refined products before departure, an elaborate system of pipes to transfer the oil through the refinery, facilities for loading and dispatching the products, plant to create energy to power the refinery, facilities to control and monitor the processes. A refinery's function is to convert crude oil into a host of useful products, and to achieve this conversion in the fullest and most efficient possible way. The industry's chemists and engineers strive to make the most from their oil. Like refining itself, theirs is a continuous, never-ending process.